Hi friends, let us learn now again graph searching algorithms. As in previous lectures we have studied DFS, now we are going to learn BFS. Okay, that is called breadth first search. Remember that we are getting the similar kind of outcomes in this, like we will be getting a cyclic graph, a spanning trace to check the reachabilities of the node, connectivity of the nodes. And in the previous lectures I already discussed that adjacency matrix, so no need of discussing again. So let us discuss what is breadth first search. Okay, just I am giving you examples such a way that you can correlate with that particular concept, right? What are the things we are going to discuss? So let us see that here we have A, B, C, D, E, F. Let us see, this is the example. If you are going to write their adjacency matrix, how it looks like, here we have A, B, C, D, E, F, A, B, C, D, E, F. A to A 0, A to B, so A to B is 1, A to C is 1, A to D is 1, A to E is 0, F 0. B to all 0 except E, C to all 0, D to all 0, E to except F all 0, and F to C and D is 1, remaining all are 0. So this is the adjacency matrix we have discussed in the previous sessions and you are knowing already. Now what basically here we are going to discuss in BFS. In DFS I said you that a stack you are going to use as a data structures. We are going to insert again and again new element, what are the new connectivities we are having it, okay, from the source to other vertex. If there is an adjacent vertex, we are going to insert into the stack, okay. But here we are going to use concepts called queue as a data structures. Remember, DFS are going to use stack as a data structures, while in breadth first search we are going to use queue as a data structures. How these working procedure are different is, first say A is a source vertex, so we will call it as A is already visited. So we can say that visited of A is already 1. If you call it, take it as a array index, means it will be 0, 1, 2, 3, 4, 5. Now whatever the direct connectivity you are having it, direct connectivity means, look, in depth first search we gone A to B, B to E, E to F kind of things. But since name itself is breadth first search, if there is an adjacent vertex from the source, from that particular node, then we are going to visit all neighbor adjacent vertex first. We are not going and searching the depth way, we are just searching towards adjacent node. If there is a connectivity, we will take it that. So A to B, A to C and A to D we have. So we will have one queue. So this is a queue array, and here since A to B, then A to C we have and A to D we have. 3 neighbor A to B, A to C and A to D we have inserted into the queue. Remember that queue has a property called first in, first out, as you have studied in DS, data structures. First in, first out. Among this, B, C, D, which is the first node, friend? B is the first node. So we are going to delete B from Q, and whatever the connectivity we are having B to other vertex, we are going to push it into the Q or insert into the Q from the rear end. From this end, we are going to delete the element, it is called front, okay, and from this side we are going to insert the element. So let us see that. B to E there is an edge. So E we are going to insert and hence B is deleted. Now once B is deleted, which is the first node to be deleted? C. So before deleting it, we are going to check that do you have any path from C to other vertex? No, we don't have it, right? Anyhow, we are going to remove it from that queue. If there is a path from C to other vertex, we'll insert it. Okay. Since it is not there, we are not taken care of. From next is D. Do you have any path from D to other vertex? No, right? So no need of inserting it here. Only we can remove this D. Do you have any path from, what is the node here? E. Do you have path from E to other vertex? Yes. And what is that? F. So we are going to insert F. Sometimes we are going to remove E. Now we are at F. From F, do you have any other path or edge or vertex which is not visited in the past? Point to be noted. We are going to insert the element in the queue which is not visited earlier. Okay. So F to C, but C was already visited. So we will be having visited array, we will be having queue. Okay. So we are going to insert the element in a queue only when that particular node or vertex is not visited in previous step. But here C is already visited, so we are not going to reinsert it. What about next? F to D, but D is already visited, so we are not going to insert it. Hence, this is done. There is no further path from other vertex. It means we already performed the task. In that case, what will be the outcome of this? Outcome of this is A we have, B, C, D, E and F. This is what our outcome is from BFS. Our outcome is from BFS after implementing BFS. Remember, if same scenario would have there in case of DFS, then what would have the answer? Since you are already becomes expert now for DFS, DFS says depth first search. So just I am writing how both are different. Look, depth first search will be starting journey from A. Do you have path from A to other vertex? Yes. B, what is other vertex? B to other vertex is E. So we are going for E, right? And from E we have other vertex called F. We are coming to F. Look, A to B, B to E, E to F and F to C. Again you have path from F to C. And do you have C to other vertex? No. Again backtrack it. Do you have any other path, further path from F? Yes. What you have? F to D. So again remember that friend, this is also minimal spanning trees. This is also spanning trees. Both the graph says that graph is connected. Here also, here also. From this we can see that from A to all the vertex is or nodes are reachable. Here also. But orientation of the graph is different. Look, we don't have path here from F to C and F to D. But we have A to C and A to D. Here we have path from F to C and F to D. But A to B and A to C and D is missing. But this is the outcome of DFS implementation. This is the outcome of after applying BFS. Okay. So that is why I said you that it's not necessary that we'll be getting the similar kind of outcomes. So all the vertices that are adjacent to a starting vertex are visited first. We have done it. We have done it for this A to B, A to C and A to D. This is the meaning of that. Then all the unvisited edges, two edges apart from it are visited. Okay, and data structures are used is Q. So from here we have visited E. Then from C we don't have any path. From D don't have any path, only E, E to F, right? Q are initialized with traversal, a starting vertex, and In that case, we have taken a start vertex this, right? And on each iteration, the vertices that are visited are added to the queue that I have shown you with an example, and after that front vertex are removed from queue. So this is already I shown you with an example. Look, if you wanted to compare DFS and BFS, since we have studied both, with respect to data structures, in DFS you are using stack, in BFS you are using queue. Number of vertex ordering, it is 2 ordering, it is a 1 ordering. Okay. Edge type, it is tree and back edge, it is tree and cross edge. Applications, we are going to find connectivity of the nodes, acyclicity. Remember that when you are saying that acyclicity, I am talking about a spanning tree 2. Okay. A spanning tree 2. And efficiency of finding adjacent nodes with using DFS, I already discussed that it will be theta v plus e, and similarly here also will have theta v plus e, that I will show you, right? But when you are reading the input in a program, so it is a 2-dimensional arrays, hence it will be, since 2 nested for loop, n square will be the time complexity. Now let us see that how BFS, breadth first search algorithm or program works. First, we are going to read number of nodes. So in particular examples, number of node was 6. Then we are going to read input from 0 to n vertex, right? It is A is 0, B is 1, C is 2, so and so. And this is the agency matrix that we have already taken up, and we wrote the agency matrix. Enter the source vertex. In this particular case, source we have given 0, that is nothing but A. For A we have given source as a 0, and initially visited of all is 0. So here we have visited of arrays. Initially we are just making visited of 0 is 0, 1 is 0, 2 is right 0, 3 is 0, 4 is 0, 5 is 0, right? So that's it. A, B, C, D, E, F, okay, 6 nodes. So we are keeping visited of all the nodes 0. Then we are calling BFS functions. Once you are calling BFS functions, it will take you to the functions BFS. Now look, we are just initializing queue. Okay, so we have another data structures is a queue. And again we will have the same things, right? Let us see that how it will move. Front is 0, front is here. Since it is queue, we have front end and rear end, and rear is pointing, rear is beginning, we are kept as a -1. It means when you are going to insert new node, it must be inserted at the place of not -1, -1 plus 1. It means we need to do the pre-increment index of rear. But while you are deleting the elements, no need of pre-increment, we will go with post-increment. Okay, because front pointer is already made it as a 0. Okay, and let us see that visited of source is 1. So if visited of 0, it is A. So visited of source is 0. So we are going to make it is 1. It's already visited, source is visited. Now under this Q of plus plus rear is equal to source. See here, plus plus rear. Okay, it means what? Pre-increment. Rear was -1 plus 1 is 0. So Q of 0 is equal to source. Q of 0 is equal to source, and source is 0. Not 0 index, it is 0 for A. We are calling it a 0 for A. Okay, so here A we are considered as 0, B we are considering as a 1, C we are considering as a 2, D we are considering as a 3, E is 4, and F is 5. This is just because we cannot give input like A, B, C, D. So we can give either 0 to n -1 or 1 to n. Next, Look, this part basically it is while, these all are inside while. Okay, so just I will help you out. This is basically while front is less than equal to rear, and these all are inside this loop. What is called node is equal to q of front post increment plus plus, right? And thereafter we are having this for loop. Inside this while loop, for I is equal to 0, I less than n, I plus plus, and inside this we are having this two condition, a of node of I is equal to 1 and wasted of I is equal to 0. So this particular statement is here. Okay, and thereafter we are going to talk about these two lines. So let us see that. Okay, now we did till here, we done with this. While front is less than equal to rear, what was front? 0. And what is new rear? Rear is pre-increment, already increment happened, 0. Both are 0. Is 0 is less than 0? Yes, equal to 0. Hence, node is equal to q of front plus plus. So what is the value of node friend? Node is equal to q of front plus plus. Q of front plus plus. So now at this point of time, f and r was visiting same things. Now f is increases to these positions, right? And that value 0 is stored in node. So at this moment node is 0. Node is 0. Now if that is case, then you are writing for I is equal to 0, I less than n, I plus plus, node is 0 and I start from 0, 0 0 is 1. So in that case we have to go to the graph. 0 0 is 1, no, 0 0 is not 1, hence there is no path, condition fail. Okay, so next additions, what will happen friend? We are going to check with another input. I increases, so 0 0 is not 1, 0 0 is not 1, so this condition is fail, right? Hence we are not going to perform this task. If only condition is true, then only we are going to perform the task, right? Okay, so now again I increases, I becomes 1. So let us see that. Here we have while front less than is equal to rear, and inside we are talking about node is equal to q of front plus plus, and here we are talking about 4, right? I is equal to 0, I less than n, I plus plus, if a of node of I is equal to 1, right, is equal to 1, and wasted of I equal to not wasted 0, then we are going to do these things. Wasted of I is equal to 1. Okay, wasted of I is equal to 1. We are going to do wasted of I is equal to 1 and q of rear is equal to I. So we are going to increase the rear pointer. Q of plus plus rear is equal to I, right? So these things we are going to repeat again and again in order to complete the task. So why I would rewrite it again? Let us see that node at the beginning, as I said you, node this value holds 0, node holds 0, 0 0 is not 1, it is 0, condition fail, will not do this. Again I increases, so for I is equal to 0 fail, I is equal to 1. Let us see that 1 1 0 1. Do you have path from 0 to 1? Yes, it is A to B, right? For your understanding I will rewrite the example such a way that you can understand in better way. Let us see that it is E, and here we have F, and from F it is like this. So wherever we are talking about 0, it is A, 1, 2, 3, 4, 5. So look, 0, 0 don't have, 0 to 1 we have a path, condition true. B is visited earlier, no, we will see that 0, 1, B is not visited. So both the condition is true. If both the condition is true, then we are going to do this. What is that? Visited of I is equal to 1. And what is I? I is 1. So visited of 1 is equal to 1. Visited of 1 is equal to 1. We are going to do that. Visited of 1 is equal to 1. Next, Q of plus plus rear means rear pointer you have increased and put I into the Q, right? Rear pointer you increase, rear was here, now rear increases, rear also came to these positions and we have inserted I, okay? So F and rear both are pointing to the same place. Let us see that what will happen next. Now I increases, so for I it is been done, for I is equal to 2. If I is equal to 2 is nothing but 0, 1, 2. Do you have path from 0 to 2? Yes. Okay, so 0 to 2 there is a path, so this condition is pass. About this condition, visited of 2 is 0. If visited of 2 is 0, visited of 2 is 0, hence both the condition is true. If both the condition is true, right, then we will do this. Visited of 2 is equal to 1 and Q plus rear is equal to I. Visited of 2 is equal to 1 and cube of rear plus, so rear pointing to these positions is 2I, right? So we are getting the same case A, B, C as we did it in the example. Now let us see that again I is equal to 2, it is pass. Let us go for I is equal to 3. 0 to 3, do you have path? Yes, path is there. So this condition is true. Whether visited of 3 is visited earlier? Visited of 3 is visited earlier? No. Hence both the condition is true. In that case, we are going to make visited of 3 is equal to 1. And these 3 vertex we are going to insert in. Okay. Remember the front is here, rear is increases, rear came till third positions. In this case, I is equal to 3 is pass. Now I is equal to 4. We are going with I is equal to 4. Right? If you are going with I is equal to 4, what will happen? 0 to 4. Do you have path? We can see that 0 to 4 there is no path. So this condition failed. If this condition failed, right, it means, right, we are not going to do this. Similarly, I is equal to 5. 0 to 5. Do you have path? Direct path. Direct edge? No. Hence condition failed. So for this also failed. So in this case we have 1, 2, 3. We have done with that. And in present scenarios we are having, this is the status. 4th and 5th is not visited. Remaining 3 vertex is visited like this. Now let us see that. Which is the at the front node, friend? Front is 1 and rear is, see here, rear, what is the value of rear? 3. Front is 1. So check the condition. If front is less than equal to rear, front is 1, rear is 3. 1 is less than equal to 3? Yes, condition true. Then go and write the node. Node is equal to Q front. So again you are going to write this, right? Steps. Node is equal to front plus plus. So store the values of Q of front in the node and then you perform the task. So Q of front, what values you are having it? Q of 1, value is 1. So these values you are going to store in node. So now we are going to do the, again retracing it. Node is 1, alright. And we are going to perform this task. Now 1 to all the vertex. Look, 1 to all the vertex. Do you have 1 to 1, 1 to 0? No, there is no path, condition fail. So for I is equal to 0 fail, I is equal to 1. Do you have path from 1 to 1? No. Fail. I is equal to 2. Do you have path from 1 to 2? No. Just check it. I is equal to 1 to 3. Do you have path? No. So this condition is failed for these all cases. Now 1 to 4. Do you have path 1 to 4? Yes. So we are going to write I is equal to 4. So there is a path from 1 to 4. And we are going to check that visited of 4 is 0. Then only we can say that condition is true. Visited of 4 is 0. Yes. So both the condition is true. If both the condition is true, right, then we are going to do this. What? Visited of I is equal to 1. Visited of 4 is equal to 1. And Q of plus plus rear. Increase the rear pointer and insert this. So here visited of 4 is equal to 1. And you are going to increase the rear pointer. Now rear is this place and inserted 4. Okay. Remember that this is array index. This is the actual our vertex name 0, 1, 2, 3. What you are writing in bracket, that is called vertex name, and above 0, 1, 2, 3, 4 is index. Next, still we need to check other possibilities. I is equal to 4. It is done. Now I is equal to 5. Do you have path from 1 to 5? 1 to 5 direct path? No, it is failed. So only 1, and we have already updated. Hence again you are going to check the conditions. What is front pointer pointing is 2. Now front is pointing to 2 and rear is pointing to 4. Is 2 is less than equal to 4? Yes. The node is equal to Q of front plus plus. So we are going to store 2 now. Now new iteration is node is equal to 2. And from 2 to 0, do you have path? 2 to 0? No. 2 to 3, do you have path? No. It is directional. So we don't have. 2 to 0 you don't have. 2 to 1 you don't have. 2 to 2 don't have. 2 to 3 you don't have. 2 to 4 no. 2 to 5 no. 2 to 6 no. So we don't have it. So what will happen? We'll just, if there is no path, we are just increasing the values of I. Once it is failed, then we'll go and recompute it again. Is 2 is less than or equal to 4? Yes. Q of front plus plus. Now node is 3. This is gone now. Okay. So front pointer reached to third position. Now front pointer reached to third positions here. In that case, check with that. Do you have any other path from 3? 3 to 0, 3 to 1, 3 to 2, 3 to 3? No, we don't have it. Hence, for this also, all condition fail. Hence, we are going to do node. Since it is 3 is less than or equal to 4, condition is true, we are going to do that node part. Node plus plus. Right? So, here we have 3. 3 also failed. Okay, so it was a 4 with Q of 4, 4. 4 is there and 4 to I. Do you have path from 4 to 0? No. 4 to 1? No. 4 to 2? 4 to 3? 4 to 4? No. 4 to 5 there is a path. 4 to 5. So here is node is 4, I is 5, condition is true, and 5 is visited. Visited of 5? No, it's not visited. Remember that friend, I have written somewhere as V. It is a visited. VIS, okay, VIS for visited. Fine. So visited of 5 is 0. Yes, both the condition is true. Hence visited of 5 is equal to 1, and we are going to insert these values. Visited of 5 is equal to 1, and insert these values at the place of 5. A rear pointer is this, right? And these all already deleted. Now we are having only fifth one. So let us see that next iterations. Is 5 is lesser than 5? Yes. Node. Now we have 5. So node is 5. From 5 to any other vertex is visited? Yes. What is that? 5 to 2 is visited. So 5 to 2, it is, I am writing over here, 5 to 2 is visited, but visited of 2 is 0. No, visited of 2 is 1. So this set condition fell. Visited of 2 is already 1. For D, visited of 3 is also 1. So both the time other condition is failed. Hence, we are not going to visit this node. and this kind of node which is already visited in the previous iterations is call it as a cross edge. Is call it as a cross edge, which a node is already visited in previous iterations, and hence that particular edge is called cross edge. So after this we can find that these all visited of I is 1, 1, 1, 1, 1, 1, all are 1. If all are 1, then we come to the main functions. Visited of I is equal to 0, I is equal to 0 to n. If visited of I is equal to 1, right, you call it as a that particular vertex is reachable from I, and what was the source vertex? 0. So we will write it, visited of I is equal to 1, printf node %d is reachable I plus 1. Why I plus 1? Because array index started from 0. So we can say that, okay, 1 is reachable, 2 is reachable, 3 is reachable, 4 is reachable. It means all the vertex given in the graph is reachable. Okay, or you can say that that particular graph is connected as well. Okay, but suppose in a given graph scenarios, if A would have not the vertex, source vertex, say C would have the source vertex, then what would have the answer? Only C is reachable. If B is a source vertex, then only B, E, F, C and D is reachable. A is not reachable from B. So these all vertex is reachable from B except A. So that will get the answer. Okay. Similarly, if you are taking source vertex as a E, then E is reachable, F is reachable, C is reachable, D is reachable, but not A and B. So this basically give you the connectivity of the graph, reachabilities of the graph, a cyclic graph, or you can say the spanning trees. So we can use it for use for the LAN connections, cable connections and all, to find whether particular node is visible or reachable, connected path we are having or not. Okay, so this kind of things. So this is all about your graph searching algorithms. All right. And for that reason only I said you this program and difference between both the cases DFS and BFS, since both comes under graph search algorithms, right? And example based on both the concept and programs based on both the concepts we have discussed today. We'll close here. Thank you very much. Thank you.